There's a number sitting behind everything you can see right now. 5 to 1. That's how much more of the universe is invisible compared to what you're looking at. Your hands, this screen, the walls around you. All of it, a rounding error. For almost 100 years, we've called it dark matter. And for almost 100 years, we've only ever seen its shadow. The way it bends light around galaxies. The way it holds spinning stars together when nothing visible should be able to. We've never seen the thing itself, not once, until a telescope pointed at gamma rays picked up something it wasn't supposed to, something that shouldn't exist if the universe was only made of what we can touch. And the person who found it didn't shout about it. He just wrote, quietly, that this might be the first time humanity has ever seen dark matter. Not its shadow, not its fingerprint, the thing itself. Stay with me, because what they found doesn't just fill a gap in physics, it rewrites what empty space even means. Let's go back, because to understand why this moment matters, you need to understand how long we've been standing in the dark, guessing at the shape of something we couldn't touch. In the 1930s, a Swiss astronomer named Fritz Zwicky was watching a cluster of galaxies, the Coma cluster, and doing something almost boring, just math. He measured how fast the galaxies inside it were moving, and then he measured how much visible mass was actually there to hold them together with gravity. The numbers didn't work. The galaxies were moving so fast that the cluster should have flown apart, torn itself into pieces and scattered across the cosmos like smoke. Except it hadn't. Something invisible was holding it together. Something with mass, something with gravity, but something that gave off no light at all. Zwicky called it Dunkel Materie, dark matter, and for decades almost nobody took him seriously. It wasn't until the 1970s, when an astronomer named Vera Rubin looked at spinning galaxies, not clusters this time, single galaxies, spinning like records, that the idea stopped being a curiosity and started being a crisis. Here's the thing about a spinning galaxy. The stars on the outer edge should move slower than the stars near the center. That's just physics. That's how gravity works around a central mass. The further out you are, the less pull you feel, the slower you move. It's the same reason Neptune takes longer to orbit the Sun than Mercury does. But when Rubin measured real galaxies, the outer stars weren't slowing down. They were moving at almost the same speed as the stars near the core, which, by every law we understood, was impossible. Unless there was more mass out there than we could see, a lot more. An invisible halo of something wrapped around every galaxy, providing the gravity to hold those outer stars in place. She wasn't imagining it. She checked one galaxy, then another, then dozens more. The pattern held every single time, and that's the moment dark matter stopped being a strange footnote and became one of the biggest open questions in physics. Because here's what it meant when you actually sat with it. Everything we'd ever studied, stars, planets, gas clouds, us, was only a small fraction of what's actually out there. Maybe 15%. The rest was something else. Something that has mass, that bends space, that shapes galaxies, but doesn't interact with light in any way we can detect. Not reflecting it, not absorbing it, not emitting it. Just there, silent, present in every measurement, invisible in every photograph. Think about what that does to your sense of the universe for a second. You look up at the night sky and what you're seeing, every star, every galaxy, every faint smudge of light, is the minority. The visible universe is the exception, not the rule. We built our entire picture of reality on the 10 to 15% we could actually detect, while the majority sat just outside our reach, close enough to shape everything, too quiet to ever be caught. For a long time, scientists assumed we'd catch it eventually, that dark matter was made of some kind of particle, heavy, slow-moving, barely interacting with anything. And if we built the right detector, buried it deep enough underground, shielded it well enough from cosmic noise, we'd eventually see one hit. A flicker, a single collision between a dark matter particle and something in our detector. Billions of dollars went into that search. Detectors built in old mines, kilometers underground, wrapped in lead and water and silence, waiting for something that might never come. And mostly it didn't. Experiment after experiment came back empty. Not because the science was wrong, but because dark matter was proving to be exactly what its name promised. Dark, uncooperative, a guest at the party that refuses to be seen no matter how many cameras you point at the room. So the search changed direction. If you can't catch a ghost walking through a wall, maybe you look for what happens when two ghosts walk into each other. That's the idea that leads us to Tokyo. To a physicist who wasn't hunting with a particle detector buried underground, but with a telescope pointed at the sky, watching not for a single collision, but for the afterglow of something far stranger. Because there's a theory, one of the most popular explanations for what dark matter actually is, that says these particles don't just sit there passively. Under the right conditions, when two of them meet, they annihilate each other. They cancel out. And when they do, they don't disappear quietly. They release energy. Gamma rays, the highest energy form of light in the entire universe. Which means if that theory is right, dark matter isn't just invisible. It's occasionally, briefly, violently loud. You just need to be listening in exactly the right way, at exactly the right place, for exactly the right signal. And that's what one SC, his name is Tomonori Totani, a professor at the University of Tokyo, and instead of building a new machine, he did something that sounds almost deceptively simple. He looked at data that already existed. For over a decade, NASA's Fermi Gamma Ray Space Telescope has been orbiting Earth, scanning the sky in gamma rays. The most energetic form of light in the universe, born in exploding stars and the violent feeding of black holes. Fermi wasn't built to hunt for dark matter. It was built to map the gamma-ray sky in general, but buried inside more than a decade of that data was a kind of background hum, a diffuse, faint glow that didn't seem to come from any single identifiable source. Not a star, not a black hole, not a known galaxy, just there, spread quietly across the sky. For years, astronomers noticed pieces of this glow and filed it under unresolved sources. A polite way of saying, we don't fully understand this, so we'll assume it's a lot of faint, ordinary things we can't individually pick out. Distant blazars, star-forming galaxies, the overlapping noise of a busy universe. That was the comfortable explanation, the one that didn't require rewriting any textbooks. Totani wasn't satisfied with comfortable. He went back through the data with a different question in mind. Not what ordinary things could be causing this, but what if some of it isn't ordinary at all? What if a portion of that glow was the signature of dark matter particles finding each other, colliding, and annihilating? Here's where the physics gets specific, and it's worth sitting with, because this is the part that makes the whole thing testable instead of speculative. One of the leading candidates for what dark matter actually is has a name. WIMPs, weakly interacting massive particles. The theory goes that these particles have real mass, real gravitational pull, but almost never interact with normal matter or light. They pass through planets, through stars, through you right now without leaving a trace. Trillions of them, probably, moving through your body in the time it takes to read this sentence, and you would never feel a single one. But WIMPs are thought to be their own antiparticle, which means when two of them happen to meet, a genuinely rare event because space is enormous and the odds are staggeringly low, they don't just pass through each other like usual. They annihilate. They destroy each other completely, and in that destruction they convert their mass directly into energy, following the same principle Einstein wrote into a single equation over a century ago. Mass becomes energy. Energy escapes as light. If that theory is correct, dark matter should be quietly glowing. Not brightly, not obviously, but at a specific, predictable energy level, in a pattern that traces where dark matter is most concentrated in the universe. So Totani did something meticulous. He modeled what that signal should look like mathematically if WIMPs were really out there annihilating at the rate theory predicted. Then he compared that model against the actual unexplained glow sitting in over a decade of Fermi's real data. And it fit. Not perfectly, not without questions still hanging in the air. Real science rarely hands you a clean, unambiguous yes. But the pattern matched closely enough, consistently enough, that Totani felt confident saying something no one gets to say lightly in this field. That this might be the first time humanity has actually seen dark matter. Not its shadow bending starlight, not its gravity holding a galaxy together. The particle itself, in the act of disappearing, leaving behind a trace of light as its only goodbye. Think about what that actually means. For 90 years, every single piece of evidence we've had for dark matter has been indirect. A gap between how fast something moves and how fast it should move. A gravitational pull with no visible source. If Totani is right, and that if still matters, this is the first crack in that pattern. He didn't build a new telescope. He looked harder at what we already had and found something we'd been calling noise that might actually have been the universe trying to tell us something all along. And that raises a question worth sitting with before we go any further. If the signal is real, what does it actually look like out there? Where is it happening? And why did it take until now for anyone to see it clearly enough to say so out loud? Let's talk about where. Because the where is almost as strange as the discovery itself. Dark matter isn't spread evenly across the universe, like a fog sitting uniformly over everything. It clumps. It gathers in dense regions, shaped by gravity over billions of years, the same way flour gathers into pockets when you sift it through a screen. And where it clumps most densely is exactly where you'd expect two WIMPs to have the best chance of finding each other and annihilating. Which means if Totani's signal is real, it shouldn't be scattered randomly across the sky. It should trace a shape. The invisible skeleton the visible universe is built around. And it does. The strongest concentrations of dark matter, as far as we understand them, sit in a few key places. The centers of galaxies, including our own. The Milky Way's core is thought to be one of the densest dark matter environments reachable from Earth. Galaxy clusters, like the one Zwicky studied almost a century ago, where hundreds or thousands of galaxies sit bound together by a gravitational glue mostly made of the stuff. And the halos, vast, invisible spheres of dark matter surrounding individual galaxies like an atmosphere surrounds a planet, extending far beyond where the visible stars stop. When Totani modeled his expected signal, he wasn't just asking, is there excess gamma-ray glow? He was asking whether that glow followed the shape dark matter theory predicted. Whether it was brighter where dark matter should be denser, fainter where it should thin out. Whether the energy of the gamma rays matched the mass range theory says WIMPs should fall into. That's the part that makes this different from just noticing an unexplained hum in the data. A vague glow with no particular shape could be almost anything. Some overlooked category of distant galaxy, some instrumental quirk, some statistical fluke a decade of data was bound to produce eventually. But a glow that follows a specific predicted shape, at a specific predicted energy, in the specific places theory says to look, that's not noise behaving randomly. That's a signal behaving like it's supposed to. It's the difference between hearing static on a radio and hearing static that, when you listen closely, is actually forming a rhythm. Here's what makes this moment feel different from 100 years of near misses in the dark matter hunt. This isn't the first time someone has claimed to see something. Physics is littered with signals that look promising for a season and quietly disappeared under scrutiny. A blip in an underground detector that turned out to be radioactive decay in the surrounding rock. A gamma-ray excess from the galactic center that some researchers still argue could be coming from densely packed neutron stars instead. an explanation that's boring, ordinary, and doesn't require rewriting anything. That argument, dark matter versus mundane astrophysics, is still very much alive. Scientists who've spent careers on this haven't universally embraced Totani's interpretation. Some think there's a simpler explanation still hiding in the data. That skepticism isn't dismissiveness. It's how this is supposed to work. But here's why this finding is hard to wave away entirely. It isn't one lucky data point. It's over 10 years of continuous observation from an instrument that's been quietly, reliably watching the same patch of sky the entire time. It's the accumulation of a decade of listening, finally analyzed with a specific, falsifiable hypothesis in mind. And it held up. Think about what it means to wait that long for an answer. Fermi launched in 2008. Every faint gamma ray it logged sat quietly in an archive, patient, unglamorous, waiting for someone to come back and ask it the right question. That's not a dramatic origin story. There's no explosion, no eureka moment at 3 a.m. It's a scientist sitting with over a decade of data other people had already looked at, deciding to look again. Slower, more carefully. And maybe that's the part worth sitting with the longest. We tend to imagine discovery as something sudden, but this one didn't happen that way. It happened the way most real answers happen. Quietly, in archives, in the space between what everyone assumed and what someone finally bothered to check. Somewhere in that decade of gamma ray data, dark matter may have been announcing itself the entire time. Not shouting, just present, waiting in the noise for someone patient enough to separate the signal from the silence around it. And once you sit with that, a different question starts to form. If this signal holds, what does it actually tell us about what dark matter is made of? Not just that it exists. We've known that in some form for almost a century, but what it's made of, where it came from, and whether finding it changes anything about how small, how outnumbered, how quietly surrounded we actually are. There's a part of this story that doesn't get talked about enough, and it's worth sitting with before we get to where this all leads. It's easy to hear a discovery like this and picture a single dramatic moment. Someone staring at a screen, watching a number appear that changes everything. That's not what happened here, and honestly, that's not what happens in most of real science. What happened is closer to something quieter, and in a strange way, more human. Somebody decided to trust a decade of unglamorous, patient data collection over the temptation to build something flashy and new. Fermi has been up there since 2008, doing the same steady, unremarkable work every single day. Watching, logging, not searching for dark matter specifically, most of that time. Just watching the gamma ray sky the way it was built to. No fanfare, no expectation that any particular year would be the one that mattered. And somewhere in that routine, in data most people had already looked through and moved past, the answer might have been sitting the entire time. That's the part I keep coming back to. How much of what we're looking for is already in front of us, and we just haven't asked the right question of it yet? How much patience actual discovery requires compared to the version of it we imagine, the eureka moment, the flash of insight? Most of the time, it's someone going back, looking again. Slower this time. Willing to sit with something other people had already decided wasn't interesting. There's something in that worth carrying with you honestly that has nothing to do with physics. We do this too, don't we? We look at something, a relationship, a decision, a version of ourselves from a few years ago, and we decide early on what it means. We file it away. Nothing new here. And most of the time, we never go back. We trust our first read of it and move on, the same way astronomers trusted for years that the extra gamma ray glow was just distant galaxies we hadn't individually cataloged yet. But sometimes the answer was never in the noise. It was in a signal we dismissed too early because we weren't asking the right question of it yet. I'm not saying that to wrap this up in a neat little lesson. I'm saying it because it's true, and because this discovery, if it holds, is proof that the universe rewards a very specific, unglamorous kind of attention. Not intensity, not urgency. Just someone willing to sit with what's already there a little longer than everyone else did. Now, where does this actually leave us? What happens next if Totani's signal survives the scrutiny already underway? The honest answer is more looking. More telescopes pointed at the same regions of sky, checking whether they see the same pattern. More independent teams running the same data through their own models, trying to break the result instead of confirm it. Upcoming instruments, more sensitive than Fermi, built specifically to hunt for exactly this kind of signal, will get their chance to either strengthen this finding or quietly retire it, the way so many promising signals have been retired before. If it holds, and that's still an if, one worth respecting, it wouldn't just answer what dark matter is made of. It would open something bigger, because dark matter isn't just a curiosity floating out at the edges of galaxies. It's structural. It's the invisible scaffolding to the entire visible universe was built around. Without it, according to our best models, galaxies wouldn't have had enough gravity to form in the time available after the Big Bang. The cosmic web, that vast thread-like structure connecting galaxies across billions of light years, wouldn't hold together. In a very real sense, you owe your own existence to something you've never seen, made of a particle we may have only just now caught the faintest trace of. Sit with that. Every star that had to form for the elements in your body to exist. Every galaxy that had to hold together long enough for a solar system, a planet, a version of chemistry stable enough to eventually build something like you. All of it, scaffolded by something invisible, something we spent 100 years chasing with nothing but its shadow to go on. And maybe, just maybe, we finally heard it whisper back. There's a particular kind of quiet that settles in when you really sit with a fact like this. Not the loud, dramatic kind of awe you get from a meteor shower. Something you can photograph. This is quieter. It's the awe of realizing that the vast majority of everything has been sitting right next to you this entire time. Passing through you, actually, right now while you read this. And for almost 100 years, all we've had were its footprints. Maybe, for the first time, we've caught it mid-step. If you've made it this far with me, if you're still here, still turning this over in your mind, I want to ask you for something small. Subscribe. Come back tomorrow. We do this every single day here, chasing down the questions most people never get a straight answer to, and I genuinely love to have you back for the next one. And while you're at it, I want to know something, not just a comment for the sake of a comment. If trillions of these particles really are moving through your body right now, invisible, silent, outweighing everything you can touch by 5 to 1, does that make you feel small? Or does it make you feel like you're part of something bigger than you gave yourself credit for? Tell me honestly, I read these. Okay, back to it. Because there's one more layer to this, and it might be the strangest part of the whole story. If Totani's signal holds up, if this really is a dark matter, finally caught mid-annihilation, it doesn't just confirm a theory. It reopens a door that's been closed for decades. The door to actually build in a complete map of the universe. Not the 10 to 15% we can see. All of it. Here's what I mean. Cosmologists have spent the last century building models of how the universe formed, how galaxies clustered, how everything got from a hot, dense point at the beginning of time to the vast, structured cosmos we live in now. And every single one of those models has had a placeholder in it. A variable labeled essentially unknown invisible mass behaves like this, we assume. A guess dressed up in enough math to be useful, but still fundamentally a guess. If we now have a real signal, a real particle, or at least real evidence pointing toward what kind of particle it is, that placeholder starts to get replaced with something measured, something tested, something we can actually build on instead of assume. That matters more than it might sound like it does, because right now, some of the biggest open questions in cosmology trace directly back to that placeholder. Why do galaxies have the shapes they have? Why some regions of the universe are dense with galaxy clusters, while others are almost completely empty, vast cosmic voids stretching for hundreds of millions of light years? Why the universe's expansion is speeding up instead of slowing down, a separate mystery entirely, tied to something we call dark energy, not to be confused with dark matter, a different invisible piece of the puzzle we may talk about another day. All of these questions get sharper, more answerable, once you know what dark matter actually is, instead of just knowing that it's there. It's the difference between navigating with a hand-drawn sketch of a coastline and navigating with an actual, measured map. You can get somewhere with the sketch, but you can only trust it so far. And there's something else worth mentioning, something that quietly changes how we search going forward. If WIMPs really do behave this way, meeting, annihilating, releasing gamma rays at a specific, predictable energy, then we now know exactly what to look for and where. The next generation of gamma ray telescopes, some already being planned, some already under construction, can be built and pointed with intention instead of hope. Instead of scanning the whole sky and waiting to notice something strange in a decade of accumulated noise, they can hunt directly, deliberately, for this exact signature. That's what a discovery like this actually does, even in its uncertain, unconfirmed state. It doesn't hand you the final answer. It hands you a sharper question, a direction to point every future instrument in. 100 years of we don't know, narrowing for the first time into we might finally know where to look. And maybe that's the part that deserves to sit with you longer than any technical detail. For almost a century, dark matter has been the ultimate example of something we couldn't see but had to believe in anyway, because the evidence around it left no other explanation that made sense. We built an entire field of science on trusting something we'd never once observed directly. And now, for the first time, that trust might be starting to pay off. Not with certainty, not yet, but with a signal, with a direction, with a decade of patient, unglamorous data finally answering a question nobody knew to ask it a few years ago. We are, all of us, living inside a universe that is mostly made of something we can't see, can't touch, can't feel pass through us. And for the first time in 100 years, we might have just caught it in the act of quietly announcing itself. We're not there yet. This is one signal from one team still waiting on confirmation from instruments and researchers who have every incentive to prove it wrong if it is wrong. But it's the closest we've ever gotten. Here's what I keep thinking about. After everything we've walked through together, you started this video the same way you started this morning, surrounded by things you could touch. A screen, a chair, your own hands, the ordinary, visible 10% of everything. And somewhere in the last however many minutes, that stopped being the whole picture. Because right now, as you sit here, something is moving through you. Not slowly, not occasionally. Constantly, silently, a substance that outweighs everything you ever held, everything you've ever loved, everything you'll ever build, by a ratio of 5 to 1. And for almost 100 years, the only proof we had that it existed was the shape of its absence. A gap in the math. A shadow with nothing we could point to as the thing casting it. Until, maybe, now. A scientist in Tokyo went back into 10 years of data other people had already looked at and decided not to trust the first read of it. He asked a sharper question of something everyone else had already filed away as noise. And in doing that, he may have caught the universe's best-kept secret in the middle of quietly announcing itself. We don't know yet if it will hold. I told you that honestly, and I'm not going to pretend otherwise now just to give you a cleaner ending. Real answers rarely arrive all at once. They arrive in signals, in directions, in gaps that get narrower instead of closing all at once. But maybe that's not disappointing. Maybe that's actually the most honest, most human way discovery has ever worked. Not a single blinding flash of certainty. 100 years of patient, unglamorous attention, finally starting to pay off. You are living inside a universe that is mostly invisible to you. That was true before this video, and it'll still be true after it ends. What's different now is that you know it. You felt the size of it, even for a moment. And I don't think that's something you unfeel. If this found you at the right time, if any part of the last hour gave you something to sit with, subscribe and come back tomorrow. We do this every day, chasing the questions most people never get a real answer to. And if it moved something in you, send it to 5 people who'd want to feel this small and this big at the same time. Tell me the truth in the comments. Not a reaction, the truth. Does knowing this change anything for you? And tell me what you want us to go looking for next. We're listening. Because somewhere out there, in data we've already collected, in a signal we've already dismissed as noise, the next answer might already be waiting. We just have to be patient enough to look again.